Welcome to the third chapter of my series on my personal exploration with squircles. This video is going to expand concepts in base P trigonometry using the maximum norm, which we discussed in chapter 2. I'd like you to recall p-norms from chapter 2. If you don't know what a p-norm is or haven't seen chapter 2, click the iCard in the top right corner of this video. On that note, I'd like to make a correction from chapter 2. At the very end, I put up a visual that indicated that the radius of any infinite degree squircle was the absolute value of r sub p to the p. It is actually just the absolute value of r sub p. Now, just taking an infinite degree unit squircle here, we can see that it's represented by this equation, the maximum norm of the vector xy equals 1. In polar coordinates, we can apply the maximum norm to our definition of height in terms of the p-norm. The p-norm of cosine and sine as p approaches infinity becomes the maximum norm of cosine and sine. We can simplify this expression further. The reciprocal of the maximum of a set is the minimum of the reciprocal of the set's elements, which is something that can be proved using inequalities, but I won't demonstrate that here. With this definition of height base infinity, we can define the other base infinity trig functions. Now, looking at these definitions, I also want to take a look at the visual definition of tangent and cotangent on the unit circle. Really take it in before I move on. Now let's look at the visualization of sine and cosine base infinity on a unit squircle. Remember that sine base p is defined as the height of this triangle, and cosine base p is the length. If we take a look at the region between the angles negative pi over 4 and pi over 4 radians, that right wall is the tangent line from our circle on the previous slide, where the sine distance from the x-axis is tangent theta. What I'm showing is that the value of sine base infinity is either tangent, 1, negative tangent, or negative 1. For cosine base infinity, it's a similar case, 1, cotangent, negative 1, negative cotangent. Shifting gears a little bit, you might have noticed the similarities between the infinite degree and the first degree squircle. If we overlay them, we can notice the qualities that make the squircles different, their distances from the origin, and their rotation. The infinite degree squircle's flat side has a distance of 1 from the origin, while the first degrees has a distance of 1 over root 2. And if you rotate this image, it's like the first degree squircle becomes the infinite degree one and vice versa. So in order to turn one into the other, one needs to rotate and be scaled. Something like this. Algebraically, this relationship looks like this. Height base 1 of x is just height base infinity rotated by pi over 4 and scaled by 1 over root 2. From this, we can derive some new equations. Multiply both sides by sine plus cosine. Then, using the angle sum formulas, the right hand becomes sine of x plus pi over 4 or cosine of x minus pi over 4. Using Heip's periodicity, we can match the argument of Heip with the cosine. If you're confused about this step, please watch the first identity break. This gives the result that sine base 1 of x plus cosine base 1 of x equals sine base infinity of x plus pi over 4, which also equals cosine base infinity of x minus pi over 4. Through a similar process, we can multiply both sides by sine minus cosine, use the angle sum formulas, and Heip's periodicity to get that sine base 1 of x minus cosine base 1 of x equals sine base infinite of x minus pi over 4, which also equals negative cosine base infinite of x plus pi over 4. These three results concerning the first and infinite degree squircle are part of what I call the Squircle similarity theorem. These statements show the relationship between these squircles and their trig functions. To recap, in this chapter, we defined base infinite trig functions and derived the Squircle similarity theorem. Bye!